Hello, my name is Scott Vaughn, and I'm going to make a series of videos on the mathematics of navigation because, well, this topic is just fascinating, and it's too big to make a Reader's Digest version. I'm going to call this series the Kerbal Guide to Navigating Any Planet, and this is part 1 in the series. In part 1, I will describe the reason I'm starting this series, where I made an early mistake, and what the other parts of the series will entail. I discovered this game called Kerbal Space Program, and it's been a long time since I had any interest in video games, but what's so special about this game is the way in which it accurately models Newtonian physics, both on the surface of a planet with airplanes and jets and projectiles, but also in outer space with rockets and satellites and moons and other planets. It's an entire solar system created just within this game, all with accurate physics. I've already learned a lot more math and physics than I knew before starting to play this game, and I've just gotten started. And by the way, you can learn a lot of engineering as well by building your own rockets and airplanes and trying them out. As I was learning about this game, I found a video on YouTube by Bradley Wistons where he is responding to a challenge posted on a forum for the Kerbal Space Program, or KSP Game. The challenge was to fly through a river canyon called the Yangtze River Canyon as fast as possible. The challenge is both in engineering, that is designing the fastest plane you can make, and also in having the skill to pilot it through the canyon. Because the game is called Kerbal Space Program, I thought I was going to focus more on rocket science, but flying through that canyon just looks so much fun, and I wanted to try that out too. So my first question was, how am I going to get to that canyon? At the time that I started, I didn't know that there were modifications to the game you could download that would allow you to teleport to some other location. So I just had to fly there, and I had no skill in building planes, so I really just had to use those available stock planes that were provided in the game. In his video, Bradley mentioned the coordinates of the mouth of the Yangtze River in terms of latitude and longitude, and that got me thinking, perhaps I could calculate the direction I should fly from the runway at the Kerbal Space Center to get to the Yangtze River. So I discovered there are formulas to compute the initial course heading to fly from any point A on the surface of a spherical planet to any other point B in the shortest time possible. And what was also interesting to me about these formulas was that the size of the planet doesn't matter. In the game KSP, the home planet is called Kerbin. Kerbin is much smaller than Earth, so it was interesting to discover the same formula that would work for navigating on Earth will work on Kerbin, and would also work, for example, on Mars, or on the planet Duna in KSP. And it was all without reference to the size of the planet or moon. This is what is so important and beautiful to me about mathematics. We're going to be looking at the ultimate truth of the nature of 3D space, and in this series, how those truths apply to navigation. And this is all based on pure, abstract, mathematical truth, and is logical and self-consistent. And furthermore, we can use the resulting principles and conclusions to make discoveries about the real world and make falsifiable predictions about what we'll discover. That is, we can use these ultimate truths to do science. What we find to be truth mathematically will be true for any planet, for Earth, for the Moon, for Mars or Venus, or any spherical planet anywhere in the entire universe, and it's even true in made-up imaginary models of three-dimensional universes like in the game Kerbal Space Program. Now, I have to admit, I didn't fully understand or appreciate some of the basic principles of navigation when I started this. I've already posted and subsequently deleted 2 videos on this topic because I discovered some things I was saying weren't exactly true. I had made an honest mistake. I didn't fully realize the significance in navigation of maintaining a constant heading versus following a great circle path, but this is where experience, even experience in a simulated world of this video game, and also the power of mathematics are both so valuable. Both provided a reality check when my experience in the game, navigating on the planet, didn't exactly match the math. I could use math itself to navigate through those questions that arose and find my way along a path to a position with some better grasp of this ultimate truth. These truths of math are really objective reality. They govern the everyday lives of all of us, whether we know it or not. These are the facts that would be true for anyone playing Kerbal Space Program, for anyone navigating the real Earth, or even now those who are piloting a rover, let's say, for example, on Mars. I like to think I'm really a pure mathematician, but even for a pure mathematician, experience provides inspiration for some foundation, and it inspires questions, and, well, the applications just keep us connected to reality. So here in part 1, I've now got the introduction done. Next, I want to finish off this part 1 by showing my first steps at some of the mathematics of navigation on a spherical planet, and some of the questions that arose, and the answers. Here we'll look at great circle paths and rhumb lines and compare those. In part 2, I'll look at the derivation of the formula for the initial heading for the great circle path. In part 1, I'm just going to use this formula, but in part 2, I'll get into the derivation and show why that formula works. I'm not sure how many parts this series will stretch into, hopefully at least 2, but if there is a part 3 or more after that, I can do more with calculating and comparing great circle paths and rhumb lines. I could look at the derivation of a rhumb line formula, perhaps even get into the math of map projections, and all of this is in a game that's called Kerbal Space Program, so it'd be hard to resist also going off into space. So, okay, maybe space navigation if this continues. Okay, so now that I have the introduction out of the way, let's really start the Kerbal Guide to Navigation. We'll look at heading and distance and time between points on a sphere. So to begin this part of the discussion, we'll have to recognize that when you choose to go in a particular direction, you could measure that as an angle from north. So you could begin north as being either 360 or 0 degrees up here. And then you could circle all the way around 360 degrees to indicate the direction you want to travel. For example, going directly east would be 90 degrees, going straight south 180 degrees, going west is 270, and any direction you want to measure between 0 and 360 degrees, you could give one single number relative to north to indicate your direction. Now, I'm going to have to refer to the idea of a bearing, which is a direction to your destination, and then a heading, which is the direction you're actually facing at that moment. So those are two different things to establish. You might begin a trip by saying, what is the bearing to our destination? And then you would determine exactly what course heading you want to follow. Do you want to follow that initial bearing or, something else? And then the question of adjusting your heading as you're going along the trip is another story. You can see that this is a picture looking down at an airplane. Looks like this airplane has a heading of 55 degrees. If it was going at 90 degrees, it would be going east, south 180, 270 is west, 0 or 360 is straight north. So for example, if you wanted to travel from Philadelphia to Miami, it isn't really directly south. It's actually a little bit west of south, about 198 degrees if you want to take the shortest route to Miami. The straight shot on the surface of the Earth is actually, you need an initial heading of 198 degrees to make that trip. It's about 1,000 miles. If you're going in a typical airplane, maybe 450 miles an hour, it's a little over 2 hours. Imagine if you were going Mach 3, take you 27 minutes to do that. But if you're going on longer trips on the surface of the Earth or any planet, there's a difference between a great circle route, which is this sort of purplish color path, and the constant heading path, which is what's called the rhumb line path. So a great circle is any circle on the surface of a sphere that has the same center as the center of the sphere. A great circle path is an arc or portion of a great circle. Like this from point P to Q, that is a great circle path. It is an arc, a portion of a great circle. The great circle path is the shortest distance between 2 points on the surface of a sphere. And a rhumb line, also called a loxodrome or Mercator track, is an arc crossing all meridians of longitude at the same angle. That would be the angle beta in the drawing here. So each time we cross a meridian, a line of longitude, it's the same angle. The rhumb line is a path with a constant heading as measured relative to north. So on a standard Mercator map, the rhumb line appears straight and appears to be the shortest distance between 2 points. Like here in this map from New York to Paris, it seems like the shortest distance would be along this dotted line. Actually, that's not the shortest distance. It's a little shorter to go this way because you're actually on the surface of the sphere, on the surface of the Earth. The Great Circle track is shorter. In fact, the rhumb line distance is always greater or equal to the Great Circle distance. Whenever I say rhumb line, I can't avoid thinking about rum, and it's not that kind of rum. The word rhumb comes from Latin, same origin as the word rhombus, and from French, and it just means a direction on the compass. Here we're looking at a Great Circle path in red and a rhumb line path in light blue. And what's so striking about this particular image is that you could see that on a two-dimensional map, the red curve seems, the red, path seems very curved, whereas it's not so curved on the surface of the Earth. In fact, it is the shortest distance. It is the straight line path on the curved surface of the Earth. And this light blue path, it seems straight on the two-dimensional map, but in fact, it's actually very curved on the three-dimensional surface of the Earth. Here's another picture of the same effect, where the path here is from Los Angeles to London's Heathrow Airport, and the shortest distance would be along the Great Circle. And you can see that would be a shorter distance there from Los Angeles to London. But the rhumb line is a straight path on the map, and it's actually a longer distance on the surface of the Earth. Here's another example. Imagine flying from New York to Tokyo. You might think you just go east, maybe just a little bit south, or maybe you'd want to go west and just come out over on this side. But in fact, actually, this trip is much longer than going north and west over Canada and Russia and then down into Japan that way. That's the Great Circle heading. 333 degrees is the direction that you would set as your initial bearing and follow that straight course off over Canada and Alaska down to Japan that way. That would be the shortest distance. And you can see that in this picture here that actually does seem shorter to follow that path from LaGuardia Airport in New York to Narita's airport in Tokyo's Narita Airport in Japan. In fact, if you look back at the other image, this is a path that goes through Spain and the Mediterranean and the Middle East and then across China. So if you're going to follow that path, in fact, you're coming way down over Spain and the Middle East, or the Mediterranean, and then the Middle East, and then China, and all the way up that way. So this is clearly a longer path to go this way. And it'd certainly be a longer path even if you went west and followed around on the other straight line distance with a constant heading. It would take longer, and it would be a further trip, any other trip besides going on this Great Circle path. This is a really neat website that will allow us to look at lots of examples of Great Circle and rhumb line paths and compare them. So it's just a fun website to play with. You can move these points around and see how that affects. So if I was to stay just going straight north, the rhumb line and the Great Circle are the same, but that's it, unless I was out on the equator. In that case, the equator is an example of a Great Circle. So there, the Great Circle path and the rhumb line are the same. Suppose you want to fly from New York. Let's zoom out. Maybe you want to go to Thailand. So that's actually shorter to go up over the North Pole and then come down over Russia. Not that you necessarily could. Maybe there's restrictions on airspace. But if you want to go the shortest route, that would be it. Pretty neat. Fun to play with. Okay, now at this point, I think I can explain one very subtle point that I did not fully understand or appreciate when I started this whole adventure. To follow the Great Circle path from some point A to some point B, for most trips, the heading will constantly change. The only time it wouldn't change is if you were traveling straight north or south, or you were traveling along the equator. In those cases, you could maintain a constant heading and also travel on a Great Circle path. In those cases, the Rum Line and the Great Circle path are the same. But for most trips, to navigate the Great Circle path requires constantly adjusting your heading. At every point along the trip, a navigator would need to establish the current bearing to the destination based on the current position and adjust the heading to travel in that direction. This is difficult and time-consuming in practice. Therefore, in real life and in Kerbal Space Program, it's just easier to travel on a constant heading. So for a long-distance trip, a navigator would determine the initial bearing of the Great Circle path, but then choose waypoints along that path and navigate to each of those points with a constant heading. So I will end this video with some clips from those original videos that I had made before. In each of these examples, I had calculated the initial bearing for the Great Circle path and mistakenly thought I should maintain a constant heading to fly to those destinations. Now, in the first trip, the distance is so small, the error wasn't really noticeable. And on the next trip, to visit the desert pyramids, I realized I had determined my initial course heading, and I maintained that heading. And when I arrived a little bit off course, it wasn't really a problem because I wanted to land on the flat desert anyway. I didn't really want to go right into the mountains, which is where my Great Circle path would have taken me. But then on the final trip, I wanted to see a UFO that was buried near the North Pole. I calculated the initial heading for the Great Circle path, and when I missed the destination because I had constantly maintained a constant heading, originally I thought, well, maybe it was because I'd gotten off course because I didn't set the right heading right away, right off the runway, but I was a little off the runway. I was a little bit away from the Kerbal Space Center when I actually finally got the correct heading, and maybe that was the reason that I was off course. But now I know to travel the shortest path to some destination, I would actually have to continually change the heading to actually fly straight on the surface of the planet. It's counterintuitive, but it's correct, and I can prove it with the KSP game. I love that I can check my math with a video game. Okay, so again, here are the formulas that I am actually using to calculate the Great Circle initial bearing from point A to point B, and it'll be a whole another video, part 2, where I go through the derivation of how did I get these formulas and where did they come from and why does it work. Okay, so what you see here is applying those formulas to a particular example, one that we've already seen, mapped out. Number 1, the initial bearing and initial heading for the shortest route from New York to Tokyo is about 333 degrees and can be computed as follows. So we need to get New York's latitude and longitude, Tokyo's latitude and longitude, and then to find the initial heading, we get the difference in the longitudes, the terminal minus initial longitude, and we're going to use that angle in this calculation for the y and x that I need to compute this angle beta prime. Now I'm going to go through the derivation in part 2. I'll talk about exactly why this is the way it is. It's a whole story in and of itself. It takes quite a while to explain. I'm going to just do the calculation here. We get us the way that I have written it out. I got the answer from the inverse tangent in degrees, and so I know that I actually basically, since this came out negative, I know that the direction is somewhat to the west, and so I subtract it from 360, or add the negative value to 360 to get the answer. 332.9, or about 333 degrees, from this 2-argument arctangent function mod with the 360. That's how it corrects from part of the process of setting it so that north is your 0 degree. Again, I'm going to go through all of how it works in part 2 when I get to that, but that's the calculation that you would do, and the answer is 333 degrees. Now, maybe if you're going to try this on a calculator yourself, it's possible that when you do the two-argument arctangent, you actually get the answer in radians. And if you're getting the answer in radians from this function, then you have to do mod with 2 pi, and then you have to multiply 180 over pi, as I had shown in the PowerPoint. You see, this is probably the way you would actually need to do it if you're going to use like Excel to do the calculation. It's probably going to default to radians, and if it's in radians, you have to do mod 2 pi and then convert it to degrees if you want the answer in degrees, which is a little bit more readable, immediately understandable what that angle is if you see it in degrees. Okay, that's the example. And you see, it gave us this initial heading 333 degrees that you can confirm. Actually, this is from another website. This is from this website called Great Circle Mapper, and I've typed in LGA to NRT, that's LaGuardia to Narita Airport, and I'm getting this path, and as you scroll down you'll see the initial heading 333 degrees. Now it also gives me this magnetic heading because I think that the magnetic north isn't the same as like the true north, and that's a whole complicated thing that I'm not going to get into right now, maybe for another video part 10 whenever I get to that. So anyway, that's the initial heading if you were going to go on the shortest distance. Now, if you're going to go on the shortest distance, you can't keep that same heading. It would actually change. Your angle to the North Pole, you can see, would certainly change as you follow that path. And so to follow that path, really the thing to do would be to probably get a few points along the way that you could fly toward with constant heading. So you would approximate that path with a bunch of rhumb lines that would be easy to follow because a rhumb line has a constant heading. So to really follow precisely and exactly the Great Circle path would require constantly updating your heading, and maybe you would a really sophisticated computer system on an airplane maybe could actually do that. But we can't do that in the Kerbal Space Program. There's no mod for that, not yet. And this would be easier to maintain a constant heading and approximate that path. Okay. Now, we just did an example on the surface of the Earth for the trip from New York to Tokyo. And I'm going to use exactly the same formulas to figure out the shortest path from the Kerbal Space Center to the Yangtze River in the game Kerbal Space Program. So it's a completely different size planet, completely different locations on that planet, and it's the same math, which is one of the points that I really want to highlight, is how this is a universal truth with respect to the geometry of a sphere and traveling the shortest path on a sphere. So the Kerbal Space Center is at 10 degrees south latitude, just below the equator, and 74.6 west. And the Yangtze River is at 22.3 north and about 38.6 west. So again, I get this delta theta, the difference between the longitudes. So this is the terminal minus initial. Get this 36 degrees, which is then used in computing this y and x numerator and denominator that we use in the inverse tangent. In the inverse tangent, I get 55 degrees, and because that's positive, I know that that is actually east. I have to fly east, and so you just take that as the answer. You could actually say that in this mod with 360, you end up with 55 degrees. So 55 degrees is the initial heading that you would take to fly to the Yangtze River. And I did that trip, and I mistakenly thought to keep a constant heading. And I got to the mouth of the river a little bit north of really where I was supposed to be. Really, this particular location, these are the coordinates of this sort of like home base where you would launch or you would start the race. Well, I was a little north of that, and I just didn't really appreciate it. I thought, well, maybe because, again, I didn't exactly start right at the Kerbal Space Center with the 55 degrees. It took me a little while to get onto a 55-degree heading. Maybe that was the reason that I was a little bit off. Actually, that's not it. I was actually curving slightly north as I continued to maintain the 55-degree heading. This is a clip from the first video I made flying on my way to the Kiangsi River, mistakenly thinking I should maintain a constant heading of 55 degrees. When I finally get there, I'm a little bit north of where I should be according to the coordinates I had used as my target would have been these islands in the bay up there. And I'm a little north of that, but it doesn't really bother me because I thought, I'm not following an exact perfect path anyway. But of course now I know that this constant heading would take me a little north of where I wanted to be. Well, once I made it to the Kiangsi River, I thought, okay, I'll start traveling around the planet, see some other sights, and, well, the next target I picked was just to fly across from the Kerbal Space Center runway, which is right here. I would just fly over to this island because there's a runway over there, and I'll just try landing. And I was really having a lot of fun with this, and so I started to add music into these trips, and so I just want to share that because it's just so much fun. Discovering how to add music, and it just makes it fun. So this is that short trip. Initial heading is 120 degrees, and of course it's such a short trip that there's really no real distinction between the Rum Line path and the Great Circle path, and in fact it's only part way into the trip where I actually have to change the heading anyway to try to line up with the runway. So, you just don't really notice the difference between a constant heading and actually taking the shortest trip. It's just really neat to see that in the game you'll see 120-degree heading takes me straight to the island, and that's just really neat. So and this is just showing off kind of what the game looks like and how it works and how much fun it is. So that's what this is. Now this is another trip I made in an earlier video. I had calculated the initial Great Circle heading of 263 degrees, and this is correct. It is the initial heading I would need for the shortest path to the pyramids. My mistake was to stay on that constant heading, thinking that that would take me to the pyramids. And the effect, since 263 is a little bit south of direct west, the effect is that with that constant heading, the true path on the surface of Kerbin will veer a little south from my intended target. And this is exactly what happens. I didn't think much about it at the time. It turned out I was better off a little south of the pyramids anyway, because that's a good landing spot. I wouldn't have wanted to fly exactly straight to the target. It would have put me in the mountains. So I want to share this video, some clips from this trip, because it was just so much fun discovering the pyramids, and just wanted you to see what that looks like also. Okay, so here's the trip to see the UFO, and this is where one really important truth about navigating on the surface of a sphere finally began to dawn on me. My mistake. I thought I should calculate the initial heading for the Great Circle path and then keep that heading to reach my destination. But the truth is, to follow the shortest path on the surface of a sphere requires continually updating your heading. That's true unless you're traveling directly north or south or traveling along the equator. In those special cases, the shortest trip will have a constant heading, but generally that's not going to be a particular path that you would choose. I mean, generally that's not what happens. So I calculated an initial Great Circle heading of 353 degrees to get to the UFO, and that's actually correct. That is the initial heading. And then as I tried to both fly straight and keep a constant heading, which is actually impossible on this particular path, I missed the target. This time it was more obvious than in the other trips before, and further, because the UFO is really small, it became hard to find when I was off course. There's a moment in the video when I zoom out to get a look ahead to where I'm going, and I realize I'm off course, and then I'm too far to the east, heading a little more toward the North Pole, when I knew that the UFO was a little bit further west. And at the time I was thinking, again, maybe this is just because I didn't immediately get onto the correct heading right off the runway, and that might explain missing the target. Well, that wasn't it. The fact is, following a constant heading, I would spiral toward the North Pole, and actually that even happened in one of the attempts that I made that I didn't record. In the video, I just correct the path and land near the UFO. Also, I have to say, this is the first time that I had gone searching for some royalty-free music to download to include with the video, and this song that I chose is actually called An Honest Mistake. It's by a band called Nihilor. I don't know if I'm pronouncing that right, but I found it on this website called Free Music Archive, and it seemed to fit, but I didn't realize how really well that music fit. And that's the reason part 1 of this series is called An Honest Mistake, and that's why I have this music playing here. The Great Circle initial heading to the UFO was 353 degrees. However, maintaining this heading does not lead straight to the UFO. The Rum Line heading to the UFO is about 340 degrees. The Rum Line path is not the shortest distance, but it is easier to navigate. With the Rum Line, maintaining a constant heading will lead straight to the destination, in this case to the UFO. So it is possible to calculate that Rum Line heading, that constant heading that you would use to reach your destination. And probably I would put this into like part 3, because this by itself is a big calculation, but I just want to show what it looks like, what the calculation looks like. So this is the latitude and longitude for the Kerbal Space Center. This is the latitude and longitude for the UFO. And here I'm calculating this phi 2 and phi 1. This calculation right here adjusts for the distortion of the Mercator map. And so basically I'm just getting how much over and how much up you need to be on the map, but take into account the stretching of the map. So I get this change in the longitude here, and this delta psi, which is this ln of this tangent ratio of tangents. Get again an inverse tangent about 70.5 degrees, but that's this angle here, so I add 270 to figure out actually the Rum line heading. So it's between 340 and 341 degrees, so approximately 340. When I do the trip, I'm going to sort of go between 340 and 341 because I can't get exactly 340.45 on the heading. All right, let's take a look, see how it goes. So again, I think next for part 2 of this series, I will derive the formulas for the initial bearing for the Great Circle path. But remember, navigating the Great Circle path is not really practical because it requires constantly adjusting the heading. But then again, the Great Circle path is still important because it is the shortest route. So a good navigator will make some compromise between the Great Circle path and the Rum Line path. Here, I'm just flying the Rum Line path to see if it works, and find out it takes about 5 minutes longer than the Great Circle path. I think if I get to a part 3 for this series, I'll do some comparisons between Great Circle and Rum Line paths for maybe a couple of different trips, and then if I get to a part 4, maybe I would derive the formulas for the Rum Line heading. Alright, but I think that's enough for now. So you can see the target starting to show up there ahead because I left the plane that I flew before at the location of the UFO. Like, I recovered the pilot, but the plane was still there, so it's easy to see where the UFO is. It's right ahead. And as I follow this Rum line, it takes me right into it. So there it is. UFO and the plane right down there. Okay, that's the end. Thank you very much for watching. I hope you enjoyed it.